Okay, so a quick recap of vector arithmetic. This is not part of your book. The book is very comprehensive. It has a lot of information, and I really like the book. But I think the book is written at the level of AS, not BS. So the math is very limited. I don't want a lot of math either, but they are choosing the optimum situation of every condition. So they are not going into any vector arithmetic or anything. In power system, vector things quantities are mostly many quantities are expressed in terms of vectors, like force, like torque, and other quantities. But again, in the book, they are taking the optimum value of that optimum situation. Like if the force is acting, they are taking that it is acting in a specific direction always, and that's how they are discussing it. So we're gonna be discussing this is a supplementary topic. We're gonna be discussing vector arithmetic, specifically dot product and cross product. As you saw earlier in the first section, for example, work of course is a dot product, force is a vector, it's not a cross product or dot product, but you saw that torque is a cross product. Um, so likewise, you will see some of the laws in chapter number 2 that you can get using cross product. You will see some of them that you can get using dot product, or some of them will simply be vector multiplication. So it's important to understand the difference between different vector arithmetic techniques. The standard vector notations that we will use, XYZ axis, is this. So X is coming out or going in into the page. Y is going to be right or left. Positive will be right, negative will be left. X will be positive coming out, X will be negative going in, and Z is going to be up and down, positive Z up, negative Z down. So each vector in 3 dimension can be broken down into its components along X, Y, and Z axis. As you can see in this diagram, these are called unit vectors, I, J, and K. I is a unit vector along x-axis, J is a unit vector along y-axis, and K is a unit vector along z-axis. What is a unit vector? Basically, unit vector is a vector that defines the direction of a vector, but its magnitude is 1. So the sole purpose of a unit vector is to define the direction of a vector. Like we discussed earlier, area vector. Area vector is a unit vector. It defines the direction of the area, which is a vector perpendicular to the surface of the area. But its magnitude is 1. So a unit vector always has its magnitude 1, and its direction defines the direction of the vector. So when we break down a vector in a space into XYZ component, we write the vector down in terms of the magnitude of the vector times the unit vector along the direction in which we are breaking it down. So I, J, and K. So if you look over here, right here, if A is a vector in a space, then A can be broken down into the magnitude along x-axis, I represent the direction along x-axis, magnitude along y-axis, J represent the direction along y-axis, and AZ represent the magnitude of the vector along z-axis, and K represent the direction of the vector along the z-axis. So this is a standard form of writing a vector quantity in Cartesian or rectangular form in 3 dimension. If you have only 2 dimensions, then you have only Ij or Jk or Ik, whatever. So what is dot product? Earlier we discussed dot product is between the 2 vector is calculated as magnitude of the first vector times magnitude of the second vector times the cosine of the angle between them, right? Now it is important, cosine of the angle between them means, remember, cosine 90 is 0 and cosine 0 is 1. That means if both the vectors between which you are taking dot products, they are parallel to each other, that is the angle between them is 0, then the dot product between them is going to be maximum, and that will be only the magnitude of the first vector times magnitude of the second vector, because cosine of 0 is going to be 1. If both the vectors are perpendicular to each other, then the cosine between them is going to be 90, the angle between them is going to be 90 degrees, and cosine will be 0. So when two vectors are perpendicular to each other, the dot product between them is 0. You don't really have to calculate the dot product if the two vectors are perpendicular to each other. So look at this example 1.3. We have a vector A and we have a vector B. Both are defined in the Cartesian form, and their components along x-axis, y-axis, and z-axis, and we have to calculate the dot product between them. So here we calculate the dot product, and the way you're calculating the dot product is simply how you multiply each component of a vector or a number, basically like a complex number or anything. So you multiply 4i by 7i, then 3j, then 9k. So 4i dot 7i, 4i dot 3j, 4i dot 9k. And likewise you do the same with 5j and 6k. Distribute it over, multiply it with the vector b. Now we just discussed, if the two vectors are parallel to each other, the angle between them will be 0, and the dot product between them is going to be the product of their magnitude. So I dot I, of course, they're the same vector, they're parallel to each other. That means the angle between them is 0, and the dot product will simply be 4 times 7, 28. I dot j, now they are perpendicular to each other. One is x-axis, one is y-axis. That means the angle between them is 90, cosine 90 is 0, so the whole thing is going to be 0. Likewise I dot k, whole thing will be 0. So whenever you're calculating the dot product, the only component that you should be concerned about are the components that are parallel to each other, or the components that are in the same direction. So I dot I, j dot j, and k dot k. Rest of the stuff is going to be 0. And that's what you see over here. So you have 4 times 7, 28, and then you have 5j dot 3j, 15, and then finally you have 6k dot 9k, 6 9s are 54, right? So your final product is going to be 28 plus 15 plus 54, which is 97 right here. And of course dot product produces a scalar quantity that does not have any direction associated with it. It's also a commutative process. Irrespective in which way you are performing the dot product, your result will always be the same. Cross product, on the other hand, it produces a vector. It's a vector quantity, and the vector basically, of course we discussed that the magnitude of the cross product is going to be the magnitude of the first vector times magnitude of the second vector times the sine of the angle between the two vectors. That's the magnitude. And the direction of the vector, C vector, is basically the direction which is perpendicular to both the vector between which you are taking the cross product, right? So if you have a vector A and B, let's say vector A is along x-axis, vector B is along y-axis, then the resultant vector C direction is going to be along z-axis, which will be perpendicular to both x and y. Okay. So in the space, anytime you have two vectors A and B and you're taking the cross product, the resultant vector direction will always be perpendicular to the two vectors. Now that perpendicular direction can be, for example, it can have two direction perpendicular, let's say going up, going down, going sideways, right or left, coming in, coming out, whatever, but it will be perpendicular to the direction of both the vectors. Okay, now how do you figure out the cross product between I, j, and k? So this table is going to help you. If you're taking the cross product between I and j, the resultant is k. So if you go basically counterclockwise, I cross j is k, j cross k is I, and k cross I is j. And if you go clockwise, now counterclockwise and clockwise I'm doing based on our notation of, wait a minute, my pen is right here. Okay, so based on our notation of earlier what we did, this is your x, this is your y, and this is your z. So this is vector I, this is vector j, and this is vector k. So if you're going in this direction counterclockwise, I cross j is k, j cross k is I, and k cross I is j. And if you go clockwise, then I cross k is negative j. So you change the sign of that, the third direction. K cross j is negative I, and j cross I is negative k, right over here. Okay, so once we have this, let's do an exercise. We have two vectors a and b, and we have to calculate the cross product between them. So again, you put them together, you perform the same thing: 4i cross 7i, 4i cross 3j, 4i cross 9k, and so on and so forth. And then you look at our table, or just think about clockwise and counterclockwise. So I cross I. Now remember, cross product is what? Magnitude of A, magnitude of B, sine of the angle between them. Now if both the vectors are in the same direction, the angle between them is 0, sine of 0 is 0. So anytime you're carrying out the cross product between the two similar vectors, that is I, j, and k, that's always going to be 0, because the angle between them is 0 and sine of 0 is 0. So you can just make them 0. This will be 0. This will be 0, and this will be 0. Rest of them, 4 times 3 is 12, and I cross j is k. So 12k, and likewise I cross k is negative j right here, going clockwise. So 4 times 9 is 36, negative 36j. And likewise you can carry out all of them, and then you can add or subtract the numbers that has this, that's in the same direction, and you can get the final answer, which in this case is going to be 27i plus 6j minus 23k. Observe that the final value is a vector quantity, is not a scalar quantity, because you are carrying out a cross product. Now there's another way to calculate this. Perhaps I would say easier way is to use determinant. If you have taken, I'm pretty sure you have taken actually, because this is an advanced course and you had circuits already taken before this, and before circuits you have taken math. So you have done determinants, of course. So cross product can easily be done using determinant. So if you're doing A cross B, all you have to do is to create the determinant 3 by 3, put I, j, k in the first row, then the vector A, 4, 5, and 6, and then B, 7, 3, and 9. And then when you carry out the determinant of this, you're gonna get this result. So this is an easier way actually to carry out the cross product. Okay, and you do it, and then you will observe. I can do it real quick actually. So I, and then 5 times 9, 45, minus 6 times 3, 18. 45 minus 18 is 27, so 27i, right? And then negative of j, 4 times 9, 36, and then 6 times 7, 42, right? 42 minus 36 is 6, so, and then minus, that's minus 6, so minus and minus is going to be plus, so plus 6j, and likewise you're gonna do plus k, and 4 times 3 is 12, 5 times 7 is 35, 12 minus 35. What is 12 minus 35? Negative 32, negative 23, or 32, 23, negative 23. So you're gonna get the same result. So this one is much easier way to do the cross product. Okay, I should have put it in here, but anyways, if you watch the video, you will know. Cross product, of course, is not commutative quantity, so A cross B is not equal to B cross 8, so don't do that. And I believe this is the end of chapter number 1. I hope you will do the problems, and you will find the problems to be pretty straightforward. If you have any question, of course, you can always contact me.